Tonight, past the orbit of Neptune, past every spacecraft ever launched, past the last known planet in our solar system, something may be moving. Not moving the way stars drift across the sky over decades. Not moving the way satellites streak through a long exposure photograph. Moving the way a world moves, slowly, silently, along an enormous ellipse that takes nearly 5,000 years to complete. Most people think of the solar system as a finished map. 8 planets, a belt of rocks and ice, and a great deal of cold, empty space. That picture is not wrong, it is just incomplete, because inside that map, a small group of distant, icy objects are doing something they should not be able to do. Their orbits are all bent in the same direction, all tilted at the same angle, all aimed at the same empty region of sky. The chance of that alignment occurring by accident, as calculated from the original 6-object sample, was less than 7,000ths of 1%. Something is shaping them. You will learn how mathematicians predicted an entire planet using nothing but the gravitational fingerprints it left behind in the orbits of other smaller things. You will understand what kind of world this might be, how far, how dark, how enormous, and why it has stayed hidden for so long. And you will hear about the telescope that began its survey this year, and what the next few years may finally reveal. Let's walk into it. If you're in bed right now, let your shoulders settle a little. Let the room go quiet around you. There is no rush to follow every word. The science will be here whether you catch every detail or drift with the narration. Both ways of listening are fine. Let me start with what most of us learned in school, because it is a picture worth holding in your mind before we start pulling it apart. The solar system has 8 planets. Mercury is closest to the Sun, small and fast, circling in just 88 days. Then Venus, a dense and cloud-covered world that traps heat until its surface is hotter than a pizza oven. Then Earth, our home. Then Mars, the red one, covered in dust and ancient craters. A belt of rocky asteroids between Mars and Jupiter. Then the 4 gas and ice giants. Jupiter, the largest, with its famous storm that has been spinning for longer than human civilization has existed. Saturn with its extraordinary rings. Uranus, tilted so far on its side that it orbits the Sun nearly rolling. And Neptune, the last of them, a cold and beautiful blue world sitting about 30 times farther from the Sun than we are. Beyond Neptune, the Kuiper Belt, a wide, flat ring of small icy bodies left over from the solar system's formation 4.5 billion years ago. Pluto lives here, along with thousands of other small objects, most of them unnamed, all of them cold and slow and quiet. And beyond the Kuiper Belt, at distances so enormous that even the concept of distance starts to feel abstract, the Oort cloud, a vast spherical shell of icy debris that surrounds the entire solar system like a thin fog at its outer edges. Comets come from here, falling inward every few thousand years when something nudges them from the dark. That is the picture. 8 planets, a belt, a cloud. It feels complete. It feels ordered and well mapped, like a room that has been thoroughly cleaned and every object accounted for. For most of human history, we added to this map one object at a time. Uranus was found in 1781, discovered by William Herschel using a telescope in his back garden in Bath, England. Neptune came in 1846. Its discovery was unusual. Before anyone pointed a telescope at it, mathematicians already knew roughly where it had to be. Astronomer had noticed that Uranus was not moving quite the way it should. Something was pulling it off course in a subtle, consistent way. The French mathematician Urbain Le Verrier and the English mathematician John Couch Adams, working independently, ran the numbers and pointed to a specific region of sky where a hidden planet would have to be. A German astronomer aimed a telescope at that region and found Neptune on the first night within 1 degree of where the math said it would be. That story is important. Write it somewhere in your mind because it is about to repeat. The map felt finished for a long time. We had 8 planets, a Kuiper belt, a cloud of comets, and a detailed model that explained everything we could see. Textbooks settled into the picture. Students memorized it. The solar system seemed like a problem with a solution, but there is a difference between a finished map and a correct one. I want you to think about what it meant in 1846 to discover Neptune through mathematics alone. Leverrier had never seen the planet. He had no photograph. He had no telescope image. He had equations, and he had the anomalous motion of Uranus. And from those 2 things alone, he pointed at a specific spot in the sky and said, "Look there." And the planet was there. The feeling in the scientific community at the time was something close to disbelief, that the human mind, through pure reasoning, could reach into the dark and touch something invisible, that the same laws of physics that governed falling objects in a laboratory could, applied carefully enough, reveal hidden worlds. That feeling is available again right now. For the first time in nearly 2 centuries, the mathematics of the solar system may be pointing at something real and undiscovered. The tools are different. The object is farther. The math is more complex. But the essential situation is the same. A pattern in the orbits of known objects that only makes sense if something unknown is out there, shaping them. And in the outer solar system, something was waiting to make that distinction very clear. Before we go any further, if this kind of patient science speaks to you, a subscription means you will never miss another video like this one. Just a quiet click. It genuinely helps. And now, let us continue. In November 2003, a team of astronomers led by Michael Brown at the California Institute of Technology, along with Chad Trujillo and David Rabinowitz, pointed a telescope at the outer solar system and found something unexpected. They named it Sedna, after the Inuit goddess of the sea, who was said to live in the cold depths of the Arctic Ocean. Sedna is a small reddish world, probably a few hundred kilometers across. It orbits the Sun, as everything in the solar system does. But Sedna's orbit is unlike anything that should be there. When Michael Brown first looked at the data, he described the feeling as deeply puzzling, not the quiet puzzlement of a minor inconsistency, the deep puzzlement of something that should not exist at all. Let me explain why. At its closest point to the Sun, Sedna is about 76 astronomical units away. 1 astronomical unit is the distance from the Earth to the Sun, roughly 150 million kilometers. So Sedna at its closest is 76 times that distance. That is already more than twice Neptune's distance from the Sun. At its farthest point, Sedna swings out to roughly 937 astronomical units, an orbit so enormous that 1 full journey around the Sun takes about 11,400 years. I want you to hold those numbers for a moment. 76 to 937 astronomical units. At its most distant, Sedna is more than 140 billion kilometers from the Sun. Voyager 1, the farthest object humans have ever launched, spent more than 45 years reaching 24 billion kilometers. Sedna's aphelion, its most distant point, is roughly 6 times that. And Voyager took 45 years of constant travel to get where it is today. But the distance was not the strange part. Distances in the outer solar system can be explained. The Kuiper belt has objects far from the Sun. The Oort cloud is farther still. Distance alone is not unusual. The strange part was the shape of the orbit. Here is how objects in the Kuiper belt normally get their elongated orbits. Neptune's gravity disturbs them. A Kuiper belt object passes too close to Neptune, gets a gravitational nudge, and the nudge stretches the orbit. The perihelion, the closest point to the Sun, stays in the inner Kuiper belt near Neptune's reach. The orbit stretches outward, but its inner anchor stays close. Sedna breaks this picture entirely. Sedna's closest approach to the Sun is 76 astronomical units. Neptune is at 30 astronomical units. The distance between Neptune and Sedna's closest point is more than 46 astronomical units, nearly 7 billion kilometers. At that separation, Neptune's gravity is far too weak to explain Sedna's detached orbit. There is no mechanism by which Neptune could have placed Sedna where it is. So something else must have done it, and nothing in the known solar system had enough reach. The simple answer, the one Michael Brown said he kept returning to, was that something unknown had pushed it. Something far out. Something with enough gravitational reach to catch an object in the inner Kuiper belt and fling it into an orbit that swings nearly 1,000 astronomical units from the Sun. But that was just Sedna. One object, one anomaly. Science does not overturn established models for a single anomaly. It files the anomaly away, keeps searching, and waits to see if the anomaly was the first of something. It was. Here is a number worth sitting with before we move on. Sedna's orbital period is roughly 11,400 years. The last time Sedna was at the same point in its orbit where it is today, human civilization did not exist. No writing, no agriculture, no cities. Anatomically, modern humans had been alive for about 200,000 years at that point, but everything we call civilization was still thousands of years in the future. Sedna completed its last full orbit before any of that began. It will complete its next one long after, and somewhere in the outer solar system it continues its slow arc, unmoved by any of it. In the years after Sedna's discovery, astronomers kept looking at the outer solar system, and they kept finding more objects. Not objects like the ordinary Kuiper belt bodies, small and close and well-behaved. Objects farther out, objects with elongated orbits that stretch to enormous distances. Objects that, like Sedna, seem to have been thrown there by something. Astronomers gave them a collective name: Extreme Trans-Neptunian Objects, ETNOs. And as the list of known ETNOs grew through the 2000s and into the 2010s, something strange started to emerge in the data. The orbits were not random. Here is what random should look like. If you have 100 small objects orbiting the Sun, and nothing special is pulling on any of them, their orbits will point in all directions. The perihelion, the closest approach of each orbit to the Sun, should be spread roughly evenly around the sky, like compass needles thrown into a field and left to fall where they may. But the ETNOs were not doing that. Their perihelion points were clustered. Not perfectly, not with the precision of a machine, but statistically, meaningfully, undeniably clustered. A majority of the extreme trans-Neptunian objects had their closest approach to the Sun pointing in roughly the same direction, aimed at the same empty region of space like arrows fired from very different places that somehow all ended up pointing at the same target. I want you to picture something. Go to an open field and throw 6 sticks in the air, one at a time. Let them fall where they will. In a random universe, they will face 6 different directions. They might not even be close to each other. Now imagine doing that 6 times, and 5 of the sticks land pointing within 90 degrees of each other. You would notice. You would wonder if the field was tilted, or if the wind was doing something unusual, or if you were somehow throwing them all the same way. That is the feeling astronomers had when they looked at the ETNOs. Something was tilting the field, and the clustering was not just in one dimension, it was in 2. Not only were the perihelion points aimed at the same region of sky, but the orbits were also tilted off the plane of the solar system by an average of about 15 degrees, all to the same side. The plane of the solar system is like a flat tabletop. Most objects orbit on or near the tabletop. The ETNOs were lifting off the table in the same direction. Two independent features, both pointing the same way, both inconsistent with random motion. By 2014, astronomers Chad Trujillo and Scott Shepard had noticed this pattern clearly enough to publish a paper in the journal Nature flagging it. They were careful. They did not claim a discovery. They noted the clustering, proposed that something massive in the outer solar system might be responsible, and called for more observations to determine whether the pattern was real or an artifact of incomplete sky coverage. The paper landed quietly. It did not make headlines. Most astronomers filed it away as an interesting note and moved on. Two people did not move on. They read the Trujillo and Shepard paper and went to work. Konstantin Batygin was 29 years old in 2015. He was a planetary scientist at Caltech with a background in mathematical physics, the kind of researcher who was comfortable sitting with equations for months at a time, letting the math find things that no telescope had pointed at yet. Michael Brown was his colleague. Brown was, at that point, probably the most recognized planetary scientist in the world, though for an unusual reason. In 2005, Brown's team had discovered Eris, a trans-Neptunian object so large and so similar to Pluto that the International Astronomical Union was forced to reconsider what counted as a planet. The debate ended in 2006. Pluto was reclassified as a dwarf planet. Mike Brown became known, with a mixture of respect and humour, as the man who killed Pluto. He had even written a book about it. In late 2015, Brown and Batygin started working through the Trujillo and Shepard data together. Batygin ran simulations, thousands of them. He built a mathematical model of the outer solar system, placed hidden objects of various masses at various distances in various orbits, and asked the computer, which configuration, if any, naturally produces the clustering we actually see in the ETNOs? He ran the simulations expecting the results to come back inconclusive. He was skeptical. He had seen patterns in astronomical data dissolve into noise before, and he did not want to be the researcher who announced a discovery that turned out to be an artifact. But the simulations kept pointing the same way. A planet, not a small one. An object roughly 5 to 10 times the mass of Earth, sitting in an elongated orbit far out in the outer solar system. And here is the detail that surprised Batygin most. The planet's orbit had to be anti-aligned with the ETNOs. Its closest approach to the Sun had to be on the opposite side of the solar system from the ETNOs' closest approaches. He ran the simulation again with this constraint removed. The clustering disappeared. The anti-aligned orbit was not a preference of the model, it was a requirement. Brown then came at the problem from a different angle. He was not trying to confirm the planet, he was trying to rule it out. He looked at the existing sky surveys that had already covered large regions of the outer solar system and found nothing. If the planet existed, he could eliminate portions of the sky where it could not currently be, based on why those surveys had missed it. Every attempt to rule it out ran into the same problem. The data was consistent with the planet existing. He could not rule it out. In January 2016, Brown and Batygin published their paper in the Astronomical Journal. The title was Evidence for a Distant Giant Planet in the Solar System. They presented the clustering data, the simulation results, the anti-aligned orbit prediction, the probability calculation, and the case for a planet in the outer solar system with a mass between 5 and 10 times that of Earth and an average orbital distance of roughly 400 to 800 astronomical units. They were careful. They said this was a hypothesis supported by evidence, not a confirmed discovery. They did not claim to have found the planet. They claimed that the existing data strongly suggested it existed. The scientific community paid attention. Brown had built a career on careful claims and solid evidence. When he proposed a new planet, people listened. The man who killed Pluto was now trying to bring one back. Let me slow down on that probability because it carries more weight than it might first seem. 0.007%. That is the probability, as Brown and Battagin calculated, of the observed orbital clustering occurring purely by chance, without any hidden planet, without any external influence, just random motion among small solar system bodies producing that exact pattern by coincidence. Here is what 0.007% means in physical terms. Imagine you had 1,000,000 model solar systems, each with the same number of ETNOs scattered in genuinely random orbits. No hidden planet, no special force, just randomness. If you looked at all 1,000,000 simulated solar systems and asked, how many of them show clustering as strong as what we actually observe in the real solar system, the answer would be about 70. 70 out of 1,000,000. Roughly 1 in every 14,000 random trials produces this pattern. Let me give you another angle on that number, one you can feel in your hands. Imagine someone hands you a coin and tells you it is a fair coin. You flip it 14 times in a row. Heads, heads, heads. 14 times in a row. All heads. A fair coin produces that result with about the same probability as the ETNO clustering, around 0.006%. You would not conclude with certainty that the coin was rigged. 1 in 14,000 is unlikely, but not impossible. But you would stop trusting the coin. You would want an explanation, and you would think hard before betting on tails. The ETNOs are that coin. 14 consecutive heads, lined up in the same direction, tilted the same way, aimed at the same empty point in space. There is also something important about what happened after 2016. The 0.007% figure was based on 6 objects, 6 extreme trans-Neptunian objects, the sample available in 2016. As more surveys ran and more ETNOs were found, the sample grew. Researchers ran updated analyses with 13 objects, then more. The clustering held. It didn't dissolve into noise as the sample size increased. If anything, it strengthened. By 2024, a paper from Battagin and colleagues reported that the scenario with no Planet 9, a solar system where the clustering arises purely from randomness or bias, was rejected at roughly 5 sigma confidence. 5 sigma. That is a term borrowed from particle physics. It is the threshold at which physicists generally agree that a finding crosses from interesting to real. The Higgs boson was announced at 5 sigma. Gravitational waves were announced at 5 sigma. 5 sigma is the gold standard. 5 sigma does not mean confirmed, but it means the bar for dismissal has become very high. That is not chance. That is a gravitational signature, and a signature has a source. So what is it exactly that would have to exist to reduce this signature? Let me be careful here, because the predicted picture has changed a few times since 2016, and the most current estimates are smaller and closer than the original numbers. A 2025 study refined the predictions using a larger and more carefully selected sample of ETNOs. The updated estimate puts Planet 9's mass at roughly 4.4 Earth masses, plus or minus about 1 Earth mass. Not as large as the original range of 5 to 10 Earth masses, but still substantial. 4 times the mass of Earth. That is the same order as Uranus and Neptune, though smaller than either. Let me give that mass some weight. Earth itself has a mass of about 6 times 10 to the power of 24 kilograms. That is a 6 followed by 24 zeros. It is the weight of every ocean, every continent, every mountain range, every iron core and molten mantle, everything that makes up our planet combined. Now multiply that by 4. Planet 9 if the estimates are right, holds more than 4 times all of that. More raw material than 4 complete copies of Earth stacked together in one cold, dark, distant place. That is not a minor body. That is not a captured asteroid or an ice pebble or a distant comet. That is a world. What would it actually look like? Picture this. Planet 9 would probably not look like Jupiter or Saturn, the big swirling gas giants. It would likely be something in between, what astronomers call an ice giant or a mini Neptune. Think of Uranus or Neptune as your reference. A deep atmosphere of hydrogen and helium, cold and thick, covering a mantle of water and ammonia and methane, not as gases and not quite as ice, but in a compressed, pressurized state that behaves strangely under those conditions. A rocky or metallic core somewhere inside. It might have weather of a kind, atmospheric bands, circulation patterns driven by internal heat from when the planet first formed, but nothing you would recognize as weather from where you are right now. Now let us talk about where it lives. The 2025 estimates put the average orbital distance, what astronomers call the semi-major axis, at roughly 290 astronomical units. At its closest approach to the Sun, the perihelion, it may come into around 200 astronomical units. At its farthest, the aphelion, it swings out to around 370 astronomical units. Let me anchor those numbers for you. Neptune, the 8th planet, sits at about 30 astronomical units from the Sun. Planet 9, at its closest approach, 200 astronomical units, is more than 6 times farther from the Sun than Neptune. At its most distant, 370 astronomical units, it is more than 12 times Neptune's distance. The scale is almost hard to hold in one thought. Light from the Sun takes about 8 minutes to reach us here on Earth. It takes about 4 hours to reach Neptune. At 290 astronomical units, the average distance of Planet 9, it would take light from the Sun more than 40 hours to arrive. Nearly 2 full days of travel at 300,000 kilometers per second just to reach it. And when that light arrives, it arrives as the light of a star. A very bright star, brighter than anything else in the sky. But still just a point. No disk, no warmth, no glow you could feel on your face. Your hand held out in front of you right now can feel the warmth of the Sun from 150 million kilometers away. From 290 astronomical units, that warmth is gone completely. There is only the light. The surface temperature at that distance would be around minus 220 degrees Celsius. Perhaps colder, depending on the planet's internal heat. At those temperatures, most molecules slow nearly to a stop. Chemistry becomes extraordinarily sluggish. Water, which flows and dissolves and sustains all life as we know it, has been a rigid solid for billions of years at that depth of cold. This world, if it exists, has been in that cold and in that dark for longer than complex life has existed on Earth. Longer than the Cambrian explosion, longer than the dinosaurs, longer than anything we would recognize as alive. It has orbited in silence, shaping the paths of smaller worlds through nothing but gravity and patience. If you're still with us, you're in the middle of something genuinely important. This is one of the most interesting unresolved questions in modern planetary science. If videos like this matter to you, a like and a subscription cost nothing and mean a great deal. Now let us keep going, because the story is not done. Here is the detail that to me is the strangest and most interesting part of the entire hypothesis. Not just that Planet 9 is massive and cold and far, but how it does what it does, because the mechanism is not what most people would expect. Most people imagine gravity as a straightforward pull. A heavy thing attracts lighter things toward it. The closer you are to the heavy thing, the stronger the pull, so you might naturally picture Planet 9 sitting nearby the cluster of ETNOs, like a shepherd standing in the middle of its flock, holding them in formation through proximity. But that is not how it works at all. Planet 9 is on the other side. Let me explain the geometry carefully, because it is the part of this story that surprised even Batygin when his simulations first showed it. The ETNOs, the extreme trans-Neptunian objects whose orbits cluster together, all have their perihelion, their closest approach to the Sun, pointing in roughly the same direction. Think of that direction as a compass needle. Now imagine drawing a line from the Sun out through that needle, through the cluster of perihelion points, and continuing out the other side. Planet 9's orbit sits so that its own perihelion is on that opposite side of the line. On the other end, the cluster points one way, Planet 9's closest approach points the other way, anti-aligned, opposite, counterintuitive. When Batygin first got this result from his simulations, he thought he had made a programming error. He went back through his code. He found nothing wrong. He ran the simulation again. Same answer. Anti-aligned configuration required. He showed it to Brown, who was equally surprised. But when they thought about it more carefully, the anti-aligned orbit made a kind of deep physical sense. Think of it this way. Imagine a shepherd who does not stand in the middle of the flock. Instead, the shepherd walks a large circle around the outside of the field, always on the opposite side from where the sheep are clustered. The sheep naturally avoid the shepherd. As the shepherd moves counterclockwise, the sheep drift away from where the shepherd is about to be, which keeps them clustered on the side of the field farthest from the shepherd's path. The flock stays coherent not because the shepherd is nearby, but because the shepherd's circular path defines an area the sheep consistently avoid. Planet 9 does something analogous through gravitational resonance. As the ETNOs complete their long, slow orbits, and as Planet 9 moves through its own enormously larger orbit, the two populations interact through what physicists call secular resonances and mean motion resonances. These are not sharp, sudden interactions. They are slow gravitational conversations that add up over millions of years. Each tiny nudge from Planet 9 is almost imperceptible, but millions of tiny nudges, all in the same direction, all applied consistently across geological timescales, confine the ETNO's orbits into the clustering pattern we see. The anti-aligned orbit is what makes that confinement possible. A planet in an aligned orbit would simply disturb the ETNOs rather than corralling them. The geometry has to be opposite for the shepherding to work. What strikes me about this is the patience of it. There is no single dramatic event here, no collision, no explosion, no sudden change. Just gravity, applied over millions of years, shaping the paths of small worlds with the same quiet persistence that water shapes stone. Planet 9 shapes them by staying out of their way. I want to be fair here, because any real investigation has to take the strongest objection seriously. Not look for reasons to dismiss it, actually sit with it and see how far it goes, and there is a serious objection to everything we have talked about so far. It goes like this. Astronomers do not survey the entire sky with equal attention. When we search for extreme trans-Neptunian objects, we look at certain parts of the sky more than others. We observe at certain times of year. We use certain telescopes that have their own field of view constraints. We tend to look where the sky is dark and the density of background stars is low. We avoid the galactic plane, where too many stars create confusion. All of this is rational, but it means our census of the outer solar system is not unbiased. We are finding objects where we looked, which is not the same as finding objects where they are. The objection says, maybe the clustering pattern is not real. Maybe we just searched certain parts of the sky more carefully, and the objects we found are clustered there because that is where we looked. The pattern could be a reflection of our search habits, not a physical feature of the solar system itself. This is called observational bias. and it deserves a real answer, not a dismissal. The original 2016 paper acknowledged this. Brown and Batagen were aware of the concern from the beginning. They estimated the bias and argued that even after accounting for it, the clustering was stronger than the bias alone could explain. But they also acknowledged that their sample of 6 objects was small, and small samples are unreliable. In the years that followed, the debate intensified. A 2017 paper by a group including Corey Shankman used data from a wide sky survey called the Outer Solar System Origins Survey and argued that the clustering evidence was less convincing when the bias was rigorously accounted for. This was a legitimate challenge. It did not rule out Planet 9, but it cast doubt on how strong the statistical case actually was. Brown and Batagen responded with more work. A 2021 paper used a detailed model of the observational biases across multiple surveys, calculated what the clustering should look like if it were purely a bias artifact, and compared that to the observed clustering. The observed clustering was significantly stronger than the bias model predicted. The bias could explain some of the pattern. It could not explain all of it. Then came the 2024 analysis. A larger sample, more surveys, more careful bias corrections. The conclusion, the Planet 9 free scenario was rejected at 5 sigma confidence. Let me be precise about what this means and what it does not mean. It does not mean Planet 9 is confirmed. 5 sigma rejection of the null hypothesis means the data is very difficult to explain without something playing the role that Planet 9 plays. It does not tell us exactly what the something is. There could in principle be a clustering mechanism we have not thought of. The bias argument has been seriously addressed, and it has survived that addressing. But science does not work by proving things true. It works by failing to find ways the hypothesis is wrong, and so far the bias argument has not succeeded in explaining away the clustering. Scott Shepherd puts it honestly. The statistics are not there yet to say definitively yes or no. More objects need to be discovered, and their orbits measured more precisely. The clustering is probably real. What is causing it remains technically an open question. Here is what lifts the Planet 9 hypothesis above a single intriguing pattern. It is not one thing, it is 4 things. 4 independent features of the outer solar system, all of which fall naturally into place if a hidden planet exists, at roughly the predicted distance in roughly the predicted orbit, and none of which have a convincing alternative explanation that does not invoke something just as strange as an undetected planet. The first line of evidence is the orbital clustering we have already discussed in detail, the perihelion points of the extreme trans-Neptunian objects, all aimed at the same region of sky, their orbits all tilted in the same direction. The original observation from 2016, now confirmed at increasing confidence as the sample of known ETNOs has grown. The second line of evidence is more unexpected. It involves a population of objects in the outer solar system, with orbits tilted at extreme angles, some nearly perpendicular to the plane of the planets, and some that orbit in the retrograde direction, the opposite direction to all the planets. These highly inclined and retrograde orbits are genuinely difficult to explain. They require something to have significantly disturbed the objects that ended up in them. No known planet can reach those objects with enough gravitational force to produce such extreme tilting. But Planet 9, in the predicted orbit, can. Batagen and Brown showed in a 2016 follow-up paper that their simulated Planet 9 naturally scatters a fraction of Kuiper Belt objects into highly inclined and retrograde orbits over billions of years. Those objects exist in reality. The model predicted them. This is a second independent confirmation. The third line of evidence involves Sedna and objects like it, a small group of bodies astronomers now call inner Oort cloud objects or detached objects. Sedna's orbit, as we discussed earlier, should not be possible if Neptune is the farthest significant gravitational influence in the solar system. Something had to detach Sedna's perihelion from Neptune's reach and leave it in its current impossible orbit. Planet 9's gravity, acting over geological timescales, could do this. And since Sedna's discovery, a handful of other similarly detached objects have been found. Each one is another point on the graph that the model predicted. The fourth line of evidence comes from a 2024 study that examined a different population entirely: low-inclination trans-Neptunian objects that cross Neptune's orbit. These objects behave differently from the classic ETNOs. They do not show the same clustering, but the studies show that even their distribution is consistent with being shaped by a Planet 9 at the predicted parameters, through a different dynamical mechanism, a completely different population, a different gravitational signature, the same predicted source. I want you to feel the weight of that. In science, one line of evidence pointing at a new thing can be a coincidence. 2 lines can be an artifact, but 4 independent lines from 4 different populations of objects, each requiring a different dynamical mechanism, all pointing at the same place in the outer solar system, are very hard to explain away. 1 coincidence is noise. 4 coincidences begin to look like gravity. Let me say something about what that word, independent, is doing in this picture, because it carries more weight than it might seem. When a single dataset points at a new hypothesis, the hypothesis might be explaining the data, or it might be an artifact of how the data was collected. But when 4 different populations of objects, discovered at different times, by different surveys, with different selection biases, all point at the same thing through 4 different dynamical mechanisms, the probability that all 4 are artifacts drops sharply. Artifacts do not usually coordinate. Real gravitational influences do. That is the structure of the case for Planet 9 as it stands today. Not one strange fact. A web of strange facts, each independently woven, all arriving at the same address. Now, I want to tell you about a different answer. Not the mainstream one, but one that is worth sitting with, because it points at something deeper than Planet 9. In 2020, 2 physicists named Jakob Schultz and James Unwin published a paper that offered an unusual proposal. What if the thing shaping the outer solar system is not a planet at all? What if it is a primordial black hole? Let me be careful to explain what a primordial black hole is, because it is very different from the black holes you might be more familiar with. Stellar black holes, the most commonly discussed kind, form when a massive star exhausts its fuel and its core collapses under its own gravity. The collapse is catastrophic. A star perhaps 20 times the mass of the Sun compresses its core into a region smaller than a city in less than a second. These black holes typically have masses of several to a few dozen times the mass of the Sun. They are the remnants of stellar violence. Primordial black holes are a different category entirely. They are theoretical remnants of the very first moments of the universe, the first fraction of a second after the Big Bang, when the density of energy was so extreme and the universe so small that quantum fluctuations in the fabric of space-time could, under certain conditions, collapse into tiny black holes spontaneously, not from dying stars. From the turbulence of creation itself, a primordial black hole of 5 Earth masses would be unlike anything in your intuition. The mass of 5 Earths is substantial, but compressed into a black hole, that mass would occupy a region smaller than a grain of sand. Its event horizon, the point of no return, would be a sphere a few centimeters across depending on the mass, small enough to fit in your palm if you could somehow hold it without it destroying you. And here is what Schultz and Unwin pointed out. A primordial black hole of 5 Earth masses in a distant orbit around the Sun would produce exactly the same gravitational signature as Planet 9. The clustering of ETNOs, the detached objects, the high inclination retrograde objects, all of it. Gravity at this scale does not care about the physical form of the mass. A 5 Earth mass planet and a 5 Earth mass black hole exert identical gravitational forces at identical distances. The outer solar system would look the same under either scenario. Here is the difference. A planet reflects light. Sunlight reaches it, bounces off its surface and atmosphere, and travels back toward the inner solar system. A planet is findable because it is, in the end, a bright object, however dimly. A primordial black hole reflects nothing. It emits Hawking radiation in principle, a slow quantum leaking of energy from the edge of the event horizon. But for a black hole of 5 Earth masses, the Hawking radiation would be in microwave wavelengths, at a temperature only infinitesimally above absolute zero, at an intensity so low that no instrument we have or plan to build would ever detect it. There is no reflected light, there is no surface, there is just gravity emanating from an almost invisible point. If the thing in the outer solar system is a primordial black hole, we will never photograph it. We would only ever know it was there by what it did to everything around it. We would see the shadow, not the thing that casts it. Schultz and Unwin were careful and honest about this. They were not claiming a black hole was real. They were pointing out that the evidence for Planet 9 is equally consistent with an undetected compact object, and that this should motivate different search strategies, ones that look for evidence of accretion rather than reflected light. Most researchers still favour the planet explanation. A planet forming in the early solar system and being thrown outward by gravitational chaos during the migration of the giant planets is a natural and well understood process. A primordial black hole captured into a stable orbit around our Sun would require a coincidence of the first order, but it is worth knowing the dark twin exists. In 2025, a new paper refined the predictions for Planet 9 in a way that changed the search in a meaningful direction. The study worked with a larger and more carefully curated sample of extreme trans-Neptunian objects, applying more rigorous corrections for observational bias. It also used a more detailed model of the dynamical interactions between Planet 9 and the outer solar system, accounting for the complex resonance patterns that shape the ETNO orbits over billions of years. The results shifted the predicted parameters in a specific and important way. Planet 9's predicted mass came down, from the original range of 5 to 10 Earth masses to about 4.4 Earth masses, with an uncertainty of roughly plus or minus 1 Earth mass, smaller than before. The predicted orbit also came in. The semi-major axis, the average orbital distance, was revised down to about 290 astronomical units. Earlier estimates had placed it at 380 to 500 astronomical units. The perihelion, the closest approach, was estimated at around 200 astronomical units. The orbital period came out to roughly 4,900 years, less than half of earlier estimates that had placed the orbital period at 10,000 to 20,000 years. Now, here is why this matters in practical terms. A smaller mass means slightly less gravitational influence, but the fit to the data was still strong. More importantly, a closer orbit makes a profound difference to detectability. When an object is twice as far from the Sun, it receives 1/4 the sunlight. That reflected light then has to travel twice as far back to reach us, weakening by another factor of 4. Total brightness falls by a factor of 16 for every doubling of distance. This is what astronomers call the inverse fourth power brightness relationship for reflected objects. Planet 9 at 290 astronomical units is significantly brighter than Planet 9 at 460 astronomical units. The 2025 refinement moved the planet closer and made it easier to find, while keeping the evidence for its existence equally strong. Even so, let me be honest about what easier to find means here. Even at 290 astronomical units, Planet 9 would have an apparent magnitude of roughly 21 as seen from Earth. The human eye can see to about magnitude 6 on a dark night. Magnitude 21 is 100,000 times fainter than the faintest star the naked eye can see. You would need a professional telescope with a large primary mirror and a long exposure time to detect it at all. But a planet at magnitude 21 is within range of the best survey telescopes currently operating or coming online. It is findable, in principle, right now. Smaller, closer, brighter, easier to find, and still not found. I want to be honest with you here, because this is what actual science looks like from the inside. Not every new discovery in the outer solar system points neatly toward Planet 9. The model makes specific predictions. Many of those predictions have been confirmed, but some new objects have come in that do not fit cleanly, and they deserve to be acknowledged. In recent years, two newly discovered trans-Neptunian objects have drawn attention from planetary scientists. One is designated 2017 OF201, announced by the Minor Planet Center in May 2025. It has a perihelion of roughly 44.5 astronomical units and an aphelion estimated at more than 1,600 astronomical units, a hugely elongated orbit that suggests a complex gravitational history. The other is 2023 KQ-14, a Sedna-like object reported in Nature Astronomy with a perihelion of about 66 astronomical units and a semi-major axis of around 252 astronomical units. Both objects have been described by researchers as useful tests for models of a distant hypothetical planet. 2017 OF201 is the more discussed of the two. Its perihelion direction is not well aligned with the clustering that Planet 9 predicts. If Planet 9 sits in the orbit that Batigian and Brown describe, 2017 OF201 should be behaving differently than it appears to. Some researchers have pointed to objects like 2017 OF201 as a challenge to the Planet 9 hypothesis. Not a refutation, a challenge. An object that does not fit as neatly as the model would like. Does this rule Planet 9 out? Probably not, and here is why. Any model of a complex gravitational system will have outliers. The outer solar system has been subject to billions of years of gravitational interactions, encounters with other stars in the young galaxy, perturbations from passing giant molecular clouds, and the complex resonance history of the giant planet's migration. Not every object will have been shaped predominantly by Planet 9's influence. Some objects fell into their current orbits through other paths entirely. Think of it like fingerprints left at a scene. If a particular person was at a location, their fingerprints might be on most of the surfaces, but not all of them. Some surfaces might have been touched by others. Some might have been wiped. The absence of fingerprints on a particular surface does not mean the person was never there. It means that surface tells a different story. The model is not broken by 2017 OF201. It is complicated by it, and that complication is exactly what you would expect from a real, messy, complex solar system interacting with a real gravitational influence over billions of years, rather than a clean, simple simulation. Science refines itself through uncomfortable data. The fit between models and reality always has rough edges. The question is whether the rough edges are small enough that the overall picture holds, or whether they grow until the picture has to change. Right now, the rough edges are small, the overall picture holds. These objects do not kill Planet 9, but they prevent the story from becoming too clean. They're exactly the kind of awkward data that decides whether a beautiful hypothesis becomes a planet or becomes a lesson. Every new object is a clue or a complication. Sometimes it is both at once. There is a mountain in Chile called Cerro Pachón. It rises to about 2,680 meters above sea level in the dry, clear air of the Atacama region, one of the driest places on Earth. The sky above Cerro Pachón is among the clearest and darkest on the planet. Almost no clouds, very little atmospheric water vapor, light pollution from human settlements at a minimum. On that mountain, the Vera C. Rubin Observatory has entered the final transition into its 10-year survey. The telescope reached official operations status in October 2025. Its real-time alert system launched on February 24, 2026, already beginning to show what the instrument is capable of. The telescope is called the Vera C. Rubin Observatory. It is named after Vera Rubin, the American astronomer who in the 1970s provided the first convincing observational evidence that galaxies are suffused with dark matter, an invisible material that outweighs all the visible stars and gas by a factor of 5. Rubin was methodical, patient, and precise. She spent years carefully measuring the rotation speeds of dozens of galaxies and building an airtight case for something invisible that the scientific community initially resisted accepting. It seemed right to name the observatory after her. The Vera C. Rubin Observatory is built to conduct the legacy survey of space and time, known as the LSST. The camera at its core is the largest digital camera ever built for astronomy, at 3.2 gigapixels. A single image from this camera covers an area of sky roughly equal to 45 full moons placed side by side. The telescope's 3-mirror design allows it to swing to a new patch of sky in about 5 seconds. On a typical night, it takes around 1,000 images, each 30 to 40 seconds long, before moving on. Over 10 years, it will photograph the entire visible southern sky roughly 800 times in 6 different wavelengths of light, building a decade-long time-lapse record of how the sky changes. Think about that scale for a moment. 800 photographs of the same patch of sky, taken over 10 years, automatically compared by computer systems looking for anything that has moved, appeared, disappeared, or changed brightness. That cadence is exactly what finding Planet 9 requires. Here is the challenge. Planet 9, at 290 astronomical units, moves very slowly across the sky. In a single night, it moves perhaps a fraction of an arc-second, a unit so small that the full moon covers about 1,800 arc-seconds, and the finest detail the naked eye can see is around 60 arc-seconds. In 1 week, Planet 9 moves a tiny bit more. In 1 month, a bit more still. But the total movement over a year is still subtle enough that a single telescope observation would not reveal it as a moving object rather than a faint star. The Rubin Observatory's solution is to watch the same patch of sky night after night, week after week, and let computer systems compare each new image to every previous image of the same region. Anything that has shifted position, however slightly, gets flagged. The system is designed to generate alerts within 60 seconds of each observation. In early alert tests, it produced hundreds of thousands of transient alerts in a single night, with millions expected as the survey reaches full operational scale. Astronomers around the world subscribe to those alerts and can follow up on anything that looks like a slow-moving outer solar system object. Planet 9, if it is in a part of the sky that Rubin surveys, would drift slowly but unmistakably across the images over the course of months to years. Not a flash, not a bright object, a slow ghost, moving against a fixed background of stars, one careful step at a time. Mike Brown has said publicly that if he could have designed a telescope from scratch with the specific goal of finding Planet 9, it would look very much like the Vera C. Rubin Observatory. The camera size, the field of view, the cadence, the automated comparison system, all of it matches what the search requires. The camera does not look for brightness, it looks for patience. Scott Shepherd, the Carnegie astronomer who co-authored the 2014 paper that first clearly flagged the clustering problem, is direct about what the Vera C. Rubin Observatory can and cannot do. If Planet 9 is real, he estimates the observatory has about a 70 to 80% chance of finding it over the course of its 10-year survey. That is a strong probability, but he is careful to add that it is not a certainty. The remaining 20 to 30% of probability space exists because there are still too many unknowns. The exact reflectivity of the planet's surface, whether its current position in its 4,900-year orbit happens to be in a part of the sky that Rubin surveys well, or whether it sits near the galactic plane where background stars make the search difficult, whether its brightness is near the upper or lower end of the predicted range. 70 to 80% is encouraging. It is not a guarantee, and that remaining 20 to 30% carries its own weight. I want you to sit with what it would mean if Rubin surveys the sky for several years and finds nothing. A deep non-detection by the most powerful sky survey ever built would not immediately rule out Planet 9. It would constrain where Planet 9 could possibly be. If Rubin covers most of the accessible southern sky and finds nothing consistent with a 4.4 Earth mass object at 200 to 370 astronomical units, that leaves only a fraction of the sky unsearched, the galactic plane, where star density makes detection very difficult, and potentially the high northern sky, which Rubin does not survey. Over several years, a non-detection would also put increasing statistical pressure on the hypothesis. If Planet 9 should be brighter and closer than earlier estimates suggested, and the best available telescope cannot find it in the most accessible parts of the sky, that is information. It either means the planet is currently in a hard-to-search region, or it means the mass and distance estimates are off, or it means the clustering pattern has an explanation we have not yet found. Here is the thing that I keep returning to. Both outcomes matter. If Planet 9 is found, we gain a world. We add a 9th planet to the solar system's count. We learn that the early solar system was more chaotic and more dynamic than our current models suggest, and that this chaos threw a planet outward to an orbit so vast that no human will ever see it complete a single revolution. We learn that the outer solar system has had a hidden organizer for billions of years, quietly shaping the paths of small distant worlds through gravity and time. If Planet 9 is not found, we face something rarer and in some ways more interesting. A mystery with no obvious solution. 4 independent lines of evidence, each pointing at a gap in our understanding of the solar system, and no planet to fill the gap. That is a scenario that would force us to reconsider something deep about how gravity works at those distances, or how observational bias operates in ways we have not yet fully characterized, or whether there is a class of object in the outer solar system that we have not yet imagined. We have been in this position before. In 1846, mathematicians watched Uranus drift off course and worked backwards to predict where the culprit had to be. Astronomers aimed a telescope at that spot in the sky. There was Neptune, within 1 degree of the predicted location, on the very first night. The same logic is running again now. Different planet, different era, different instruments, but the same fundamental situation. Mathematics pointing at something invisible, and a generation of astronomers asking whether the math is right. We're in the middle of finding out. Right now, in the survey nights already accumulating on that mountain in Chile. And here is the thing I find genuinely remarkable about this moment. The answer may already exist in data that has already been collected. The Rubin Observatory generates tens of terabytes of data every night. Its automated systems flag millions of moving objects per year. Within those alerts, if Planet 9 is in a part of the sky Rubin is currently surveying, the signal is probably already there. Not found yet, because finding it requires the slow accumulation of many observations of the same patch of sky over many months. But present. A faint point that shifted slightly between one image and the next, waiting to shift again and again until the pattern is unmistakable. We may be months away. We may be years away. The answer may arrive quietly in a technical paper in an astronomy journal before it reaches a newspaper. Or it may not come from Rubin at all, but from a follow-up observation prompted by Rubin's data, a large telescope staring at a specific coordinate for a long night and finding a faint moving point exactly where the math says it should be. Let me bring this back together. We started with a finished map, 8 planets, a belt of ice, a distant cloud of comets, a solar system that felt solved and complete. Then Sedna appeared in 2003, sitting in an orbit that nothing in the known solar system could have produced. Then more objects followed, all doing the same wrong thing. Then 2 mathematicians at Caltech, Michael Brown and Konstantin Batygin, ran the numbers through thousands of simulations and pointed at an empty region of sky and said, "There is something there. Something massive. Something cold. Something shaping the paths of these smaller worlds from a distance so vast that the sun itself would look like a star from there. The world probably 4 times the mass of Earth. Orbiting our sun between 200 and 370 astronomical units, moving so slowly that one full orbit takes roughly 5,000 years, leaving its gravitational fingerprints in the orbits of dozens of smaller worlds in 4 independent lines of evidence, all pointing at the same place. We know what it should weigh. We know roughly where its orbit should carry it. We know the geometry of how it shapes the things around it. We know the fingerprints it leaves, even from a distance where no light has reached us. And we still have not seen it. That is not a failure of science. That is science doing exactly what it's supposed to do, holding uncertainty honestly, refusing to look away from uncomfortable questions, building better tools to look further, and waiting with patience for the evidence to arrive. Think about the strangeness of the position we're in. We have a mathematical prediction built from the crooked orbits of small distant objects that points at a specific region of the sky and says, "Look there." We have a telescope that just started looking, and we have a question that has been building since a small reddish world called Sedna appeared in 2003 with an orbit that should not exist. Right now, as you rest in this room, the Vera C. Rubin Observatory on a mountaintop in Chile is photographing the southern sky. The same patches of darkness night after night. Its computers compare tonight's image to last week's image of the same region, searching for anything that has moved, looking for a slow ghost in the dark. Maybe the ghost is there. Maybe the camera will find it in the years ahead. A faint point of light moving so slowly that only the long memory of a 10-year survey can reveal it. And when it is found, if it is found, it will be the same story it has always been. Mathematics reaching into the dark ahead of telescopes, finding the shape of something before the light arrives to confirm it. Or maybe the survey will accumulate years of data and the ghost will not appear. And then the real question begins. What is producing the fingerprints of something that is not there? That question would take us somewhere new, somewhere our current models do not have an answer for. Either way, something changes. Somewhere out in that cold, if the mathematics is right, a world is moving right now, in permanent darkness, lit by a sun that looks like a very bright star, surrounded by ice and silence and an orbit so large that human civilization had not yet invented writing the last time it was at this same point in its journey. It does not know it is being searched for. It has been out there longer than the Cambrian explosion, longer than complex life has walked this planet, longer than almost anything we could name. The idea that we can feel the shape of it, through the bent paths of smaller worlds, through the patient accumulation of orbital data, through the mathematics of gravity alone, is one of the quietly remarkable things that science does. It reaches past the edge of what we can see and finds the outline of what we cannot. The map is not finished. And somehow, in this particular moment of history, we are close enough to the edge of what we know to feel the shape of what comes next. The Rubin camera is running. The alerts are accumulating. The mathematicians are watching. And a world, if it is there, is moving in the dark, patient and indifferent, waiting to be found by the one species in the solar system that learned to read the invisible language of gravity. Rest well. If this video found its way into your night and gave you something real to carry into sleep, please consider subscribing. There are more quiet investigations like this one waiting for you here, and if you drifted somewhere along the way and want to start again, it will be here whenever you are ready. Good night.